Okay, everyone, let's start. I want to make sure that we can finish our lecture today. Okay, the rule of the class. Good afternoon, everyone. Good afternoon. There you go. Okay, so we're going to be done with GMM today, finally. 2.5 sessions. Yeah, you should be very happy. One of the very challenging and hardest topic in ML in general. So again, so if you have a good understanding of GMM, that would be an awesome thing for us that, okay, we understand GMM, the way it works, and how we're going to just use it in our homework. You're going to just write it in your homework as well, homework 2. Okay, so before I start, any question? Any question before I start? Any question? No question? All good? Okay. Okay, let's start. So in GMM, we initialize the parameters. What are the parameters of a GMM model? What parameters do we have there? Yes. Mu, sigma, and pi. If I have just one feature, let's say height, then sigma becomes what? Variance. And mu becomes? No, I know mu. So what is it? Is it a scalar or is it a vector? Scalar. A scalar. So what if I have more than one features? What's going to happen to sigma? Covariance. And mu becomes a vector, which means that the average value for the first feature, second, or anything that I have. Okay. So initialization. When I initialize, I mentioned that there is a good way to initialize GMM. And what is that good way to initialize GMM? Yes. We're going to use k-means to initialize the parameters, pi, mu, and sigma. And that's quite important, by the way. I'll show it to you why it is important for us to initialize it that way. So in the expectation part, what do I calculate? Yes. What's that?
What's the value for pi when you initialize k-means?
What's the value of pi when I calculate k-means? So I'm going to calculate how many data points I have within that clusters over all data points. Okay. That would be a good prior, which means that, oh, this, like, for instance, one Gaussian has many more points, which means that it should have more weight. Yeah. Yes.
How can we initialize the covariances with k-means?
So if I have a data points within a clusters, let's say I have 20 data points in one cluster in k-means. How do you calculate covariance? X bar transpose, X bar divided by N. But that X bar is 20 by D, right? Which is the number of features. Does it make sense? Okay. Any other question? No. Okay, so in expectation part, what do we calculate in GMM? In k-means, what did I calculate in the expectation part? In k-means, what did they calculate? Expectation part, yes. Distance, which means that eventually I wanted to calculate clustering membership, right? It's the same here. It's the same here. So what we calculate is called, what do I call this function? We call it responsibility, okay, which is tau, gamma, and it's quite similar to clustering membership. What is the size of responsibility? I mentioned that this one is a matrix. What is the size of responsibility matrix? It's a matrix. Anyone remembers the size of this? Who wants to help me? Yes.
Is it n by k?
N by k. There you go. K means what?
The clusters.
The number of clusters. So it's n by k. So if I put it here, let's say I have k is equal 3, which means that I have 3 clusters of component, k0, k1, and k2. What is the summation of each row? Is equal to 1. So can I consider this one as a PDF? This is the PDF. Yes, probability distribution function. This one is discrete or continuous? This is discrete, but it's a PDF for us, okay? It is a PDF. So how can I do clustering membership based on that? How do you do clustering membership? The one that has, I need to convert GMM is a soft clustering or hard clustering? Soft. So if you want to do a cluster membership, you need to convert this one into hard clustering. How do I do it? Possibly I go with the maximum. 70% belongs to that one, so probably that data point belongs to that cluster. Okay, that becomes our, what we call this becomes our responsibilities. What is the next one? After expectation, what do we have? Maximization. In k-means, what was the maximization part? I recalculated the, what was the parameter of k-means? No, k-means. The parameter of k-means was center. Remember, the centers were the parameters. So I wanted to recalculate the centers. Okay, so, but here, what are the parameters of GMM? Instead of centers, we have mu, sigma, and pi. If I have 3 components, 3 clusters, for each component, how many mu, sigma, pi I have? 3. How many not how many mu? How many parameters do I have for each component? 3. So in total, I'm going to have 9 parameters. So this means that in maximization part, I need to recalculate all the parameters, mu, pi, and sigma. Okay. And then for convergence, what do I use for convergence? We calculate the log likelihood. So we go over all data points. This is our mixture model, mixture Gaussian, GMM, Gaussian mixture model, and then we just do the likelihood function. For convergence, we do that. Okay. Any question here? Any question? So we went over this one, and this is what you need for your homework. So you got to be careful, especially calculating this one, responsibility, and calculating these from responsibility. You got to be very careful how you calculate these values from responsibilities. Yes?
When we calculate those from responsibilities, that is our lower bound?
That's a very good point. I'm going to get to that part. Very good question, yes.
Is all that math to recalculate the parameters using matrices?
Yes.
Because
Yeah.
I was thinking whenever I was studying, like that's a lot of.
That's a lot of summation. So that's why GMM, you got to be very careful. For loop is just what? In do not like list in our class, right? So you got to be careful. Some parts we got to use for loop, but some parts we can just use broadcasting or parallel processing. Okay, that's why we use NumPy for that. Any other question? No. So then I talk about general form of EM. So if you remember, I used log of likelihood. That's, remember, for convergence, we also need to calculate this one. Anytime I use lowercase l, this means the log of likelihood, right? So otherwise, I'm going to write a log, p of x given theta, and theta means all the parameters, just the notation, a generic general notation. So I have it here. So this is our linear combination of, combination of Gaussians, Gaussian mixture model. It's our mixture model. Okay, so what I had here, I introduced a random PDF, and I mentioned this one is a PDF, and I said it's a random one. It's quite important that I define it as random. I multiply everything by a random PDF, divide it down. Am I allowed to do this? Yes, because they can cancel out. And then what theorem I use to go from this equality to into inequality? We use Jensen inequality, right? In our previous session, I mentioned how we can use Jensen inequality. Remember that I did the change of variable here. Q of zk given x became p of x, and this one, g of x. So if I replace it here, what is the definition of this? This is our expected value. So, and based on a log function, log is concave, convex, or none? Log is? You got it. So log is concave. This means that this function is always above the lower bound. So log of e of x is always greater or equal e of log of x. And when I did it, replace everything. So this one is our lower bound or upper bound, this part? Upper bound. Which is our what? Which is our log? This is our log likelihood. Log likelihood. And this one is what? This one is our lower bound. And so I did also some quick investigation of what it means visually, what it means by upper bound and lower bound. Okay? So if you look at it here, let's visualize what it means by upper bound. So if I expand this one, and then you can see what? So this becomes log of Gaussian 1 plus Gaussian 2 plus Gaussian 3 and so on. Do you think this one is a concave or convex function? So Gaussian is what? Gaussian is log? Gaussian is log concave. How about log of Gaussian 1 plus Gaussian 2 plus Gaussian 3 plus Gaussian 4? We don't know. So it's just going to be a crazy function. That's the only thing we know. Because is it going to be even PDF? Gaussian 1 plus Gaussian 2 plus Gaussian 3. The area on the curve is not going to be equal to 1. It's not going to be even a PDF. And log of a crazy function becomes crazy itself. Okay, so we're going to have this crazy function which looks like this. We're not going to optimize this. Instead, what we're going to do, we're going to optimize the lower bound, and we're going to see that why this is going to help us to optimize the main log likelihood function. So QZK given X is a PDF, and let's say it's given to us. So that's why I consider this one as a constant. We don't know what type of PDF that one is. So if I just expand this one and just let's understand what is it there, it becomes log of Gaussian plus log of Gaussian plus log of Gaussian. What it means by this? Log of Gaussian is what? Concave or convex? Concave. Plus log of another Gaussian. Concave plus concave is what? Concave. And so I'm expecting this function to be concave. Is it easy to optimize? Very easy. Okay. Good. So let's see how this function is going to work and how optimizing this becomes very interesting, by the way. I'm going to flash back a little bit here. What did I use here? This function. Remember when I just, this log likelihood, when I take the derivative with respect to mu, I said I'm stuck here. So in order to make myself unstuck, what did I do? I replaced this one with what? This one was our responsibility. And I mentioned this one is our upper bound and this one is our lower bound. And now if I use lower bound, I can get a closed form solution because the function here is what? Here is not concave or convex, here is concave. But something's crazy is happening here. This one is equal to this one, upper bound is equal to lower bound. Do you see that upper bound is equal to lower bound? I'm using equality here. So how can it be possible and so on? That's a very important question that you should have. Why upper bound is equal to lower bound? Okay, so now let's answer this question. At first, if I can, let's say, I want to, theta means what for us? Theta is our parameters, and this one is our log likelihood. The reason I didn't use mu, pi, and sigma here because it would have been 3D and so on. I can't just write it and to visualize it, so I just put simply theta. So what is the first step in GMM? What do? We randomly initialize parameters, pi, mu, and sigma, here theta. Assume that we randomly initialize this one, so this becomes our theta. Okay, so, and then once this is our theta, then I can just find it here, and that's it. I mean, the problem now, if I look at this function is not going to do anything. Like even if I maximize this function at that point, let's say this point goes away from this, I can figure out this function or whatever, and then I can maximize it. This is not something that we're looking for. Again, that equality is important. I'm going to explain this some more so we understand what is happening here. Let me remove this before I explain what is the duty of this lower bound here. Do you think this one is a lower bound? This function can be considered as a lower bound at this point. Why no? Because some part of it is higher. So this one is not lower bound. How about this one? This one is lower bound? No. How about this one? Yes. How about this one? Yes. So we're not interested in any type of lower bound. I'm interested in one very specific one, right? One very specific lower bound. And what it means by that. Okay. So I initialize this one. And what I'm going to say this one corresponds to a value. Can I calculate log likelihood when I have my theta? When I have mu, pi, and sigma, can I calculate log likelihood? Yes, we can calculate it. So that's going to be a log likelihood. And I'm going to say that I'm interested. This is, by the way, there is an expression here. Don't get scared. They call them type bound. Okay? So I'm interested in one type of lower bound that has one common point with my log likelihood, with my upper bound. Okay. So let's see. Do you think this lower bound could be an option? Can be a choice. Why? Because some part of it is higher the other function. How about this one? No. How about this one right here? So there is just one solution here that lower bound can just touch. What's happening at that point? What is so specific about this point? So this means that lower bound and what? Upper bound are the same. Remember that equation when I put lower bound and upper bound became the same. That's this point that I'm interested in. Are we clear? Okay, so what do I need to do? Now I have that specific lower bound. What do I need to do with lower bound? Now we need to maximize the lower bound. When I maximize it, which value it's going to give me? Let me call this one theta 0. So it's going to give us this one. So what is the theta corresponding to this? This becomes our theta t. Now that I have theta t, can I calculate log likelihood for that theta t? So we can calculate it. It's going to give me this point. Now that I have this point, what is the lower bound that can have the type bound here? I need to move, as if it's dragging the whole thing up here. Can I say this is the one? Now what should I do with this lower bound? Maximize it. So this will give me what? T plus 1. Right? Okay. And then what should I do with this? I need to find it here. And I keep moving this one until what happens? The convergence happens. Log likelihood goes into convergence. Remember, I mentioned that for convergence, we calculate what? Log likelihood. So at that point, when log likelihood convergence happens, means that a stationary point. In the stationary point, the difference between previous step and current step should be what? When we are in the stationary point, it's going to be very small. And that's how we get to that point. And that's the duty of the lower bound. Okay, any question? Let's see. Here, yes?
Do you get the global maximum or just the local maximum?
Very good question. Okay, if I initialize my parameters, let me see. If I initialize it here, let's see what happens. So which lower bound? Tell me a stop anytime that you find with that lower bound. Stop. Okay, so now this one is going to go to the right side or left side? Left side. This means that it's going to drag right here, drag until I get to this point. Will it give me a local or global? Local. Anytime you run GMM based on your initialization, it might give you different results, outputs, yes. So if I drop it here, which direction is going to go? It's going to go to right. Okay. What is the unluckiest point here? What is the unluckiest point? Yes, you have some ideas.
Well, probably the one that's going to give us our lowest local maximum.
Local, not global. If I started from this point, that's the unluckiest point. We're going to get stuck at that minimum, right? But do you think we're going to start it at that point? How do we initialize GMM? We're using k-means. This means that we're going to start already in a very great place. So possibly once you do k-means, you are already here. Right? You are already very close to that optimal point. So there's almost zero chance that you're going to hit that minimum. Okay, any question here? Yes.
What would be the process if we started on like essentially zero, right? Like we start on the very, very far left, whereas
Yes, you can start from zero, and then what's going to happen to, you can't start, like when you use k-means, you're not going to start from zero. And some like initialization also forbidden. If you start from those, you're going to get stuck, right? So I'm not sure whether in GMM 0 is going to be one of those bad ones. It might be, I don't know. Yes?
If you're using like k-means plus plus, are you more likely to start somewhere near the local global maximum?
There is no global maximum,
Okay.
right? So we don't know whether it's a global maximum or it will give you a local solution. But what we do, we use a good optimization algorithm like EM, which will increase our chance to give us as close as possible to like hopefully the best solution. Okay, good point. Okay, so what did I mention? I mentioned that one. We're looking for a lower bound that what? This tight band happens. Okay, so how we're going to ensure here? It's going to get interesting. So here in this inequality, am I interested in inequality or equality? I want to make sure that this one is equality. Lower bound is equal to upper bound. Remember in that when I take the derivative with respect to mu, in order to go from upper bound to lower bound, I replace one term with what? I replace it with responsibility. Okay? So if I replace it with responsibility, is it a PDF? Is the responsibility a PDF? So this means that I'm not looking for any type of PDF. I'm interested in one specific one, which is responsibility. Let's assume that this random PDF is equal to our responsibility. Let me do it here. So zk given x is equal to our gamma, okay, or tau. I'm going to write it in terms of p here. It just makes sense later on. We're going to see it. So it becomes zk, the same equation, zk given x. I put theta because responsibility depends on some parameters. So you need to always put theta over there. And this is our old, something which is given to us. Okay. So let's look at this part, the lower bound. Let me write it as LB, lower bound. So this random PDF, I should replace it with what? By the way, these should be K. So what is our responsibility? What did I use? I changed it to this. Now this means that PZK given X theta, all this means our responsibility. Okay, so what should I write here instead of QZK given X? I should write it as P of ZK given X theta old. Multiply by what? Log of A over B becomes what? Log, help me. P of X, ZK given theta minus log of, we should not write Q, ZK given X. We should not write the random one. We are interested in one specific one, which is equal to responsibility. Our PDF, I assume that our random PDF is equal to our responsibility. Okay, we're going to see that it's going to make sense soon. So if this becomes P of zk x theta old. Are we clear so far? Any question? Anyone? Any question? Before I continue, I want to make sure that we are clear. Are we clear? Okay. So what I'm going to do, this term, I'm going to work on this term a little bit more. Let's work on this term a little bit more. Log of, not log part, I'm just write this term. Our responsibility. Zkx theta old. Let me know what rule I'm using here. Denominator, I'm going to use p of x theta old. Numerator, I'm going to use p of zk x theta old. What is this rule? No, be careful. Anyone, what is this rule? Exactly, P of A given B is equal to what? P of A joint B divided on by P of B. Okay? And if I want to use, and if I want to make this one P of A given B, no, we should use the other one. P of B given A mod. What rule I use to go from here to here? We use product rule, right? So if I want to use product rule down here, this becomes what in the denominator? P of x what? Okay. There you go. So I want to use this one. I want to use this type of zk given theta old multiply by what? What rule I use? We also use product rule. Can I do this? So we did it. Can I cancel out this one with this one? Okay. And over there, let's rewrite the whole thing again. Lower bound, bless you. K, P of zk, given x, theta old, log of P of x, zk theta, minus what? Log of what? I'm going to replace this term, right? I'm going to replace this term with what I calculated here. So this becomes what? This becomes? What is the numerator part? So what I have here, remember I recalculated the whole thing and used Bayes' rule and rewrote it in this way. Can I replace it here? So this becomes probability of xzk given theta old divided on by P of x given theta old. Good? Okay. Log A over B becomes what? Log of A minus log of B. Can I do it? Yes, we can do it. Anyone, are we following everyone? Are you following what I'm doing here? Yes, who is not following? Which part do you confuse?
I'm still trying to catch up from the section that's written there in black.
So this one, what I did, do you see this part?
Yes.
I just brought it here because I wanted to rewrite in a different form.
Okay.
Okay, so what did I use? P of A given B. I'm using Bayes' rule. How do I use Bayes' rule? Anything in the given part must be in the denominator. And the numerator is just going to be a big joint probability. Okay, so if I have P of A, B, and C, can I write it as P of A, B, given C multiplied by P of C? That's what I did. So this becomes AB given C. Does that make sense now? And then I can cancel out these two. And can I replace this term with this new one right now? Okay, so that's what I did. Are we back in the track? Good track? Okay, enough good track. Okay, so any other question? So I'm going to use log property here. So this lower bound becomes what? Sigma k, p of zk, x theta old. Help me here so I can write it fast. Log of p of, okay. The given theta old. Theta old. Good? Can I cancel out these two terms? Yes or no? They are the same, why not? Oh, sorry, this one should be old. I forgot to write it here. Now, can I do it? Yes. Yes, thank you. Good point. This one should be old. Okay, so what's going to happen here? This becomes p of zk given x theta old p of x. So the second term, does it depend on this summation? Does it depend on k? The second term, oops. This one, okay, this one should be old. So this means that, can I bring it behind the summation? This becomes p of x given theta old multiplied by what?
Given x theta.
Okay, so what is this one? This one is R. What did I call it? This one is R. Responsibility. What is the summation of each row of a responsibility? PDF. What is the area under curve of a responsibility? 1. So this term becomes what? 1 for us. So what's going to be our lower bound then? P of x given theta old. Let's look at upper bound. What is our upper bound? Are they the same? Yes, they are the same. Now equality happens. Okay, so if I use responsibility, you can see that equality happens, that tight bound happens. So just for responsibility, that's why I replaced that term with responsibility, so you can help me with the tight bound. Okay, any question here? Yes.
Are we, because I feel like every step of this makes sense, and it's easy to understand what's happened at each step. With it, I feel like the intuition behind why we, specifically like why responsibility causes this to, our upper bound to equal.
It's because of this calculation. In fact, it's just a mathematical calculation, right? If I put responsibility term, that just everything is just going to cancel out. So I'm going to, so if I put responsibility here, so the whole idea is, this one is, okay. The whole idea is, once I put responsibility, you can see that I go from upper bound to lower bound. But why I was allowed to put equality? Because if I put responsibility, you can see that lower bound and upper bound become the same. And I just prove it to you mathematically. Why they become the same. Okay? So it's just mainly mathematical proof here. Okay. Any other question? So we're done with, can I just say we're done with GMM? You're not done with GMM. Lecture-wise, we're done with GMM. So you're going to use it in which homework? 2. Homework 2. Is it going to just hunt you, or is it just going to just give you joy? No, come on, it's going to give you joy. I mean, all of the above. You make your life easier. Okay, so we're done with GMM. You're not done with GMM again. So why? Because you're going to use it for homework 2. And GMM is a great example of what ML is. Because we came up with this objective function, we optimized it, and we found all these optimal parameters. Okay, So I'm going to talk about completely different things. So forget about GMM just in this lecture, right? Not completely, don't completely forget it. Okay, now silhouette coefficient is an algorithm for us to understand whether we have done a good job in terms of clustering or not. Let's say if I have 2 clusters or if I have 3 clusters, which one is better? 2 clusters or 3 clusters? By the way, I did the same thing in k-means, last slide in k-means. What did I do to compare like how many clusters are good? Elbow, right? So we did elbow point, elbow point. Why? Anything before elbow was under or over clustering? Under. Anything above the elbow was over clustering. So elbow was one of them. Here I'm going to introduce something quite similar, and you can apply it for both GMM and you can apply it for k-means. Doesn't matter what the clustering or any future clustering algorithm. Okay. So how many clusters I have here in this example? We have 3 clusters. So for a good clustering, this is what Silhouette does for us. For a good clustering, the data points within the clusters, do we want them to be very close to each other or as far as possible from each other?
Very close to each other.
We want them to be very close to each other. The points across different clusters, do we want them to be very far or very close to each other? Very far. And that's what Silhouette will calculate for us. For a good clustering, a data point within the same cluster must be very close. Across the cluster must be very, or across the cluster we call them interclusters. Within the cluster we call them intra. Okay, so that's how they call them. Okay. So for this, what we're going to do, Silhouette coefficient in general, we're going to calculate, let's say here I have 1, 2, 3, 4, 5. I have 15 data points here, which means that our n is equal to 15. For every single data point, we need to calculate something which is called Silhouette coefficient, S15. Okay. Let me calculate it for one data point, and then you'll figure out how you're going to do it for the other data points. Let's focus on one data point. I want to calculate the distance of this data point from the other one within the same clusters, within the same cluster. What type of distance function I should use? Euclidean is our general choice. So, okay, so I'm going to use Euclidean. I'm going to calculate the distance from this, and so on. Mu means what for us? Mu typically means average. So what I'm going to do, I'm going to find the average distance between all of them. So that's going to give me something called mu n. I'm going to have 2 mu out because I have 2 more clusters. If I had 4 clusters, how many mu out I'm going to have?
4.
3. 1 is mu in and 3 mu out. Okay? So how do I calculate mu out 1? The distance from all of them and take the average. Mu out 1, mu out 2, the distance from all of them, calculate the average. If you look at it here, I am particularly interested in the minimum mu out. Why we are interested in minimum mu out? Why not maximum? Let me see if you have any other members. Why we are interested in minimum mu out, not the maximum? Any thoughts? Here, I want to hear from this cluster, this component. You have awesome mu pi and sigma here. You have full covariance here. Okay, I want to hear from you why we are using minimum instead of maximum. Any idea? Come on, we don't have much time. Just give me your general thoughts. Why are we using minimum 1? I'm not going to move on until one of you just tell me one thing, even if it's wrong. Why are we using minimum 1? Yes, you have something to say. Concave up. What does it mean? You would like me create a new theorem. I do it most of the times. Okay, that's okay. What else? Okay, should I shift to the other side, the other cluster? It means they have a lot of data point. Your pi is very powerful. So what do you think? Yes, back there.
would it be because, or like, we're more focused on the cluster that's closest to that data point, and if there's going to be an error, it would be with the nearest cluster.
Exactly, because we are interested in the worst case scenario. So that's our worst case scenario. If we are doing well in the worst case scenario, of course we're going to do well in other scenarios, right? So that's why we use minimum. Well, you know, collaboration of two clusters, you did it. Okay, if I can call it that way. Okay, so the way we calculated again, mu out minus mu in, and the maximum, again, worst case scenario. So we have it for every silhouette. And then once I have it for 15 data points, I need to calculate the average of all the silhouette, and it's going to give me a silhouette value, just one scalar. So a value close to 1 implies a good clustering. By the way, I'm using this notation. Anyone knows what it means by this notation? What did I calculate from this to here? What is it? Okay, this one is distance function. This is our distance function. Okay? So let's say I have Gaussian, I run it with 2 clusters with k equals 2, and Gaussian, I run it with k equals 3. How can I know whether k is equal 2 is better than 3 or 3 is better than 2? What should I do? Let's see. Yes.
Well, you could try to figure out the ratio of u in to the minimum u out.
No, we explain everything. So what did I calculate here? So I need to calculate silhouette coefficient for 2 clusters, and I need to calculate silhouette coefficient for 3 clusters. Which one I should go with? The one with the larger value, right? The one with the larger value, we're going to go with that. Okay. But there is a problem with silhouette, because silhouette, what type of distance function we're using? Euclidean, which means that it can capture spherical shape. Does it really work for Gaussian, which is mainly elliptical shape? That's why we don't have just one type of clustering evaluation that works for, so we have multiple one, right? So you got to consider multiple ones, yes.
Just to make sure, mu min out is you calculate for each data point the distance from each other
Yes.
cluster, and then
Yeah.
get the minimum of each of the cluster.
I calculate the distance from all of them and calculated an average of all these distances, right? Did the same thing, and I went with the minimum one. Worst case scenario.
Then, like, you would choose the yellow or
Exactly. I'll choose this one. Any other question? No? Okay. Can we continue? Let's go to our next class. Okay. Oops. GMM doesn't want us to leave. Okay. What? Let us leave. GMM like, no, teach me more. Okay. In k-means clustering, k-means and GMM. By the way, this one is hard or soft clustering? Hard. And this one is soft. So what is the limitation in both of them? What is the main kind of limitation there for both of them? Anyone? The main limitation. Any idea? Both of them have this issue, yes.
It's hard to know how many clusters you need going into it.
We need to know, very good. We need to know the number of what in advance? K in advance. Okay, I'm gonna introduce you a new clustering algorithm, which what's gonna happen, yes?
I have a quick question before. So when we calculated the silhouette coefficient, why did we calculate mu in if you're only taking the mins of all the numbers?
Why we calculate what?
Mu in.
Okay, because I want to make sure also the data points within the cluster are also very close to each other, and that's why we capture it.
So where does that get factored into our calculation?
In the first equation was mu in minus mu out. So I want that distance, so mu in minus mu at, and also that can be contributed in the denominator part when I use maximum. If you look at it, then you can see the effects of mu in. Okay. So I'm going to introduce an algorithm, hierarchical clustering. You're going to see it when you compare it to GMM, way, way easier. It's like a piece of cake. Okay, you're going to enjoy it. But that doesn't mean that that algorithm is bad. In fact, hierarchical clustering is one of the very good ones out there when it comes to visualization. You want to visualize your data and so on. Very good algorithm, in fact, but it's quite simpler. So that will kind of like give us this interesting point of like why we want to use it. But the good thing about hierarchical clustering, you calculate it first, and then you decide how many clusters you want, which means that post-decision making, it's not like k-means and GMM, which are pre-decision making, which I need to know the number of clusters in advance. Okay. So we're going to talk about hierarchical clustering. So if you look at hierarchical clustering, as the name implies, we're going to have a tree-based structure. So we're going to start from the bottom, and then each data point will create their own clusters, and then as I go top to the hierarchy, I'll merge them. This one is an example of k-means that I need to know the number of clusters in advance. I'm going to give you a couple of examples as motivation why we want to use it. So let's say I want to organize a bunch of CS computer science papers. If I look at this tree, typically what do we call this top node? The root. What do we call the bottom ones? Leaves. Or leaf nodes. Okay. So if you look at AI can just turn into data mining, networking, computer vision, machine learning. Do we have a class for each of them? Yes, in Georgia Tech, you can see that we have. So if you really want to be good at ML, you need to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. Like after our class, you have 9 more classes to take. Are you going to do it? You should do it. I mean, come on, ML is fun. Okay, so if I even look at machine learning, if you look at clustering, reinforcement, and deep learning, each of them also has a class, deep learning, reinforcement, and Bayesian network. So we're going to go over some important parts, but again, if you want to dive into those, you definitely need to take those classes. But again, how it is related to clustering. Give you another example. Let's say I have animal as the root here, vertebrate, invertebrate, fish, reptile, amphib, mammal, worm, insect, and crustacean. So, and the question becomes, by the way, do not call this one, in last couple of slides, I'll call them tree. Forget about this. We got to call them dendrogram. This one is called dendrogram. Quite important. If you call them tree, it's wrong. It's called dendrogram. So this dendrogram, now that I created it, we don't know how. We're going to learn it. So there is an expression we say we need to cut the dendrogram. So because I can visually see things, that's awesome for us. I can visually see them. What if I cut it here? How many cutting points I have? 2. This means that 1 cluster, and what if I want more clusters? Should I cut it in the lower part or upper part? Lower part. So I can cut it here. So how many clusters we're going to get? 7 clusters. Right? So that's quite interesting for us. Now I can do it, now visually see it, and for your project also you can do the same thing. Because you know your data points, you can visually see them, and then you can cut them in the good place. What if you don't know whether 7 is good or 2 clusters is good? What can I do to compare 2 with 7 clusters? We can use silhouette coefficient. Why not? Right? We can use simply silhouette coefficient as our clustering evaluation. I'm going to introduce you more clustering evaluation, not just silhouette. There are going to be a bunch of them out there. Okay. So give you another example. I mentioned at first, every single data point creates their own cluster. Here, how many data points I have? So, which means that how many clusters? 7 clusters. Now I need to figure out a way that finds similarities between data points. Similarities, how do you measure similarity? What typically we use for similarity measurement? Distance measurement is a good way for similarity measurement. So for instance, if I How can I find the distance of one picture to the other picture? What is a very kind of like a dumb way to do it? Finding the distance of one picture to the other one. What I can do, I can flatten this picture. It becomes what? A giant vector. Let's say this one is 20 by 20 becomes 400. This one's 20 by 20 becomes 400, and find the distance between two vectors. Is it the best way? No. Are there better ways? Yes, there are much better ways to compare, like find the distance between two photos. But let's say I do it this way, and I found that these two are quite similar to each other compared to the other one. And the average of these, or like this, the whole cluster is quite similar to black bear. And the whole thing is also quite similar to speckled bear. So what I'm creating something here, pay attention. I'm creating something called chain. So chaining is happening here. Is it a good thing or bad thing? We don't know. Depending on your data, you may want chaining, or some people may not want chaining. So how can you get rid of this chaining? There are ways that you can do it. I'll explain later. So what method we can use that we do chaining, and what method I use that I'm going to have more balanced dendrogram. I'm going to put giant panda also as a part of this chain, raccoon and red panda out of this chain, and then we have it here. Okay, good? So if I cut it here, how many clusters? We're going to have 1, 2, 3, and 4. Okay, so speaking of panda, I have always this story. I also mentioned it in the other class. I'm going to share something about panda with you. Okay, and I'm going to share something about what is the good thing, what is the good reason behind being a PhD student. Okay, when I was a PhD, or maybe I think I was a PhD student, I had this chance to just travel to many places, writing conference paper, and why not? It's paid for, your advisor pays for it, the best things ever. Just send me over there, send me over here, and so on. So I had the chance to go to China, and I went to a province called Chengdu province. If you have never been in that area, you got to be very careful. The food is very spicy, so I just I burned myself. That's hot spicy. So, but the cool thing over there, they have something called Panda Sanctuary. They have a couple of hundreds of pandas over there. And of course, I was there for a research project. I really wanted to go to that Panda Sanctuary. By the way, we have a couple of pandas here in Atlanta, if you want to see them, because they're going to transfer them back to China. Why? Because they are very expensive to keep. I'm like, okay, so just let's go back there. It's easier to maintain. And this specific panda, this one actually grabbed my attention because of one important reason. And that was quite interesting. So I was like, okay, so the people who were working there, they were just grabbing all these bamboos and taking them to this panda, like, eat, you're cute, we want to keep you alive or something. And they're so lazy. That's a part of them that, yes.
Can a panda do ML while sleeping?
You did try. That was good. Okay, so they were, so the panda, yes, and then they were taking all these bamboos, and the panda's like, okay, just let us die. I mean, we're much better than this world. I mean, so come on. And there was another panda at that time. It was actually climbing. It was very close to the top of the tree. And I asked one of the people working over there, so what's going to happen to this panda? He said, we're not going to do anything. This panda is just going to stay there because they're so lazy. They're not going to go down, and they're just going to die out of hunger. So one of us is going to go up and bring them down there. I'm like, wow, such a life they have, like a good life. And that was something over there. So I went to China, and then we had another project in Japan. So I had to go, we went to Tokyo. No, but by the way, I had this encounter too. This goat, I think it was one of them, either China or Japan. I'm not sure whether the goat is itchy or like trying to just find some. So we went to Tokyo. The good thing in Tokyo was cherry blossom. So it was very beautiful, but the thing is that when you go for a cherry blossom, what's going to hit you bad? Pollen allergy. I was crying while I was looking at these pollens, and people said, "Are you crying because so happy?" No, I'm crying because like this is a pollinator and so on. So why I'm saying this? First off, getting to know different cultures. Anytime you get a chance, that's the most beautiful thing. Like why people do it the way that they do it. Now I understand why people do it in different way in Japan, like in China. And I also had the chance to go to India. I went to Bangalore. IISC, it was one of the very good universities. That was another beautiful craziness over there, and I enjoyed it a lot. So, and what was that? I get to know different cultures, and I loved it. I enjoyed it a lot, and so I'm motivating you to be a PhD. So if you have an advisor, like my advisor, Dr. David Frost, anytime that I was like doing something, Dr. David Frost, can I write a conference paper? It's in the other country. I'm like, is it because of you want to go to that country or if you want to write the conference paper? I'm like, both of them, come on now. And so I was writing the paper, so I had the chance to go to see different countries. And so are you going to do PhD now? Anyone? No? It's not convincing enough? It's not, I guess, some of you. So I was enjoying the whole process. Look, doing PhD, you got to do it with the right advisor, by the way. Some advisor, like, you got to just write paper. I mean, just stay there and just write paper. And at the end of my PhD, I was like, Dr. Frost, can I just stay one more longer here? And it's like, no, you need to get out of my lab. I mean, you're so expensive. So you need to just start your own life. So that's why I got out of the lab. So here we are. Okay. Any question about Panda? Just messing with you. One of the students in the previous class said that, the pandas in Atlanta Zoo much more active than panda in China because they don't give them that much food, so they need to work for their food. So that's why they're more active. That was so funny to hear that. Okay. So remember we had, let's go back to our hierarchical clustering. Remember that we had these words, Peters, in different languages. And so possibly hierarchical clustering would be a very good way to organize them. Okay. So there are two ways to calculate hierarchical clustering, bottom up and top down. We're not going to use top down. It's not very efficient when it comes to computation part. So bottom up is a very good one, is computationally friendly. So we're going to use this. What does it mean by bottom up? At first, we consider every data point will create its own cluster. And I keep merging them until all data points become a part of a giant cluster, one single cluster. Top down is what? Giant cluster, and I keep splitting those until every data point becomes a cluster. Okay, how does it work? The first part, let's say I have 30 clusters here. I need to find the closest clusters with each other. What should I use? I can use Euclidean distance, right? So these two are quite close to each other. How many members do I have in each cluster? One member. Now, how many members I have in this cluster? Two. And I find the other one, and then now I need to find the distance from a cluster with one member and a cluster with two members. How do you suggest I can do this? What do you mean average of two members? Average of what?
So take like the midpoint of the 2 points.
The midpoint of the blue ones? So it's going to give me what? It's going to give me a value here, so this becomes our... There is a name for this. We call it, by the way, average link. So you just figured that out. What else? Any other thoughts? Any other idea? This was one of them. Any other way that I can measure the distance from one cluster to the other? I know that podium is over there, but you got to give me something too. This group. Any other? Yes, you're going to give me something. Tell me. Whatever comes to your mind, tell me. What is it? No idea?
I was working with an idea of probability, but I don't...
No, that's just a little bit sophisticated. So how about I calculate the distance from one data point to one of them and distance from one to the other one. So I can calculate the average. And that's called average link. What you mentioned is called centroid link, sorry. What you mentioned is called centroid link, and this one is called average link. What else? Yes.
I have a question about this actually. So if we keep merging into parent cluster, wouldn't there be a point that we just have one cluster for everything?
Yes.
How do we know when to stop?
That's the time that you stop, when you have one cluster.
But we want multiple clusters.
No, that's the point about hierarchical clustering. You decide the number of clusters at the end, post-decision making. That's why we cut the dendrogram. Any other thoughts? Yes.
Is there a reason that once we find like that first pair of clusters, or that like first pair of data points, that we try to connect to that instead of connecting other data points that are closer?
Because I couldn't find any ones which are closer, but that one is close. So this one is closest to this. If I just look at any other pairs, those are not going to be as close as this one to this cluster to the other one.
Okay.
Yeah, so we always try to find the minimum one.
Yeah, so if there was a different pair of 2 points that were like in a separate chunk of the space.
And they were closer, I would have gone with that. Okay, yes.
Could you also do, like, calculate the distance to the first point, calculate the distance to the second point, and then say that the distance is just the closest.
Okay, so there is a name for this. We call it single link. Okay, so let's go over a couple of these links. Let's say I'm going to merge A with either B or C. What did I calculate here? I calculated all the distance, but I picked one of them. Which one is that? The shortest one. I'm going to do here the shortest. If I were to merge A with B or C, which one I should go with? B. So this one is called single link. I call it the shortest of shortest. I put an S over there because shortest, because there are multiple of those. How about this one? Which one I picked? The longest. Which one I picked? So if I want to merge A with B or A with C, which one I should go with? A with C. And this one is called the shortest of the longest. And we call it complete link. So again, the worst case scenario. Longest is, because we have 2 of these. Okay. So if we use, by the way, this one is a reverse, this one is our root node, these are our leaf nodes. If we use single link, you're going to have a chain phenomenon. So if you use single link, if you use complete link, you're going to have more a balanced dendrogram. Okay? If you don't know which one you want to choose, you got to go with average link. Because again, that's really up to what type of problem you're dealing with and which one you want to work with. Okay. How we're going to do it, I'm going to do some calculation here for you so we understand how it works. So we know single link, complete link, centroid, and average link. Okay, let's do one example here. How many data points I have here? How many features? And the reason I have 2 features so I can draw everything here so we can see what is happening. At first, how many clusters I have? 5. And what I need to calculate this pairwise table. And that's why it makes this program, this algorithm very inefficient. If you have 1 million data points, then this table is going to be 1 million by 1 million. So it cannot even fit into your computer memory. So you can see that the distance from A to A is what? A to B is 1, B to A is 1. This means what? Distance function is symmetrical. Okay. So first thing first, we don't care what type of links we're using. Anytime you see this table, you got to go with the minimum value. What is the lowest distance value here when you look up this table?
0.
No, come on, no, not 0 here. Besides 0, you're not comparing one cluster against itself. 1. Thank you. So this means that which two clusters I need to merge? A and B. Now, as I go, I'm constructing, we're building what? R dendrogram. So at 1, A and B are merged. So I'm going to use average link. What is the distance of AB to C? So how do we calculate it though? AC, the distance AC plus BC divided down by 2. So let's look at it from table. ABC, 1.4 plus 2.2 divided down by 2. When you compare this one with GMM, which one is easier?
This one.
Yes, this one is like, as I mentioned, it's like a piece of cake, the way we calculated. AB from D becomes what? 3.2 plus divided down by 2, and this one. And now I have a new table. When you have a new table, what should you do with that table? You need to find the minimum. What is the minimum value here? 1.4. 1.4. Which means which one I need to merge? D and E. So let's merge D and E, 1.4 D and E. So I need to calculate the distance of DE from AB and DE from C. So DE from AB becomes 3.6 plus 4.9 divided down by 2. DE to C, 2.8 plus 4.2 divided down by 2. So I have this new table. What should I do with this? Which is? AB and C. And so I have 1.8. So what is the distance ABC to DE? 4.25 plus? Divided down by 2. So it's going to give us 3.8. And so you can see that this is my dendrogram. I have just one cluster, so I know where to cut it. Now that's up to you, how to cut it, right? So if I cut it here, how many clusters I'm going to get? 2. If I cut it here, I'm going to get more clusters. Okay, one more example, 2 more examples. These are going to be quick. Okay, if I use single link, what is the distance of AB to C? Single link is what? The shortest of the? Shortest. Just a second. So the shortest of the? Yeah. This means that the distance of AB to C is equal to AC or BC? AC. So AB to C, which one I should go with, minimum or maximum? Minimum. 1.4. AB to D, 2.55. AB to E, 4.5. What is the minimum value? 1.4, which is AB and C. Okay. So now I need to calculate AB. You can see that chaining is happening. Do you see that? Chaining is happening. A, B, C from D, which one I should go with? Minimum 1, AB to E, minimum 1. So what is the minimum value here? There are multiple options here. Are you going to do chaining? If I want to do chaining, which one I should go with?
ABC to D.
A, B, C, D. If I want to do a more kind of a balanced dendrogram, D and E. If I don't know,
Random. Average.
exactly. So you have a coin in your pocket? Yes, take it out and flip it. So that becomes a random choice. So which one I went with? D and E. So I went with D and E, and so we have it here, so we can calculate dendrogram. The last one, complete link. AB to C, which one I should go with? AC or BC? AB to C, so I should go with, how about here with D? I made a mistake here, okay, so that's a mistake. Another way that I create a new theorem. AB to E, 5.4. Which one is the minimum one? There are many 2.12. We go with the random one of them, okay? Let's say I go with D and E. If you look at this dendrogram, we keep doing this with the maximum one. The dendrogram is more stretched because we are considering larger values here. And then we have our dendrogram, so we can cut the dendrogram. Okay? So I'm going to finish it here, but I'll continue the rest of it in our next session Wednesday. Okay, Doug? Have a good one, everyone. I'll see you this Wednesday.